So there are a lot of different kinds of hypothesis tests out there that you could do, but one of the simplest, in fact perhaps the simplest hypothesis test you could conduct is something called a t-test. This is the most common null hypothesis test you'll see when you look around at the literature online, and it is basically just an inferential statistical analysis, a hypothesis test, that compares two means. So here's the mathematical equation for calculating an observed t-score. We call it the observed t-score because it's the t-value you observed by collecting data. So there are three different kinds of t-tests, but they all use this basic formula. And if you just take a look at the formula, you have the mean for group 1 minus the mean for group 2 divided by this S sub m. We'll get to that stuff in just a moment. So when you do compute a t-score, that observed t-score or test statistic, it goes by a few different names, you will need to compare your observed t-score to something we call the critical t-score, the critical value for your test. And it's by doing this kind of comparison that we determine those significance values. We determine those p-scores. So the way we make this comparison with the t-test is to look up the critical value of t in a table based on your study's degrees of freedom. And degrees of freedom can be defined as n-1. So take your sample size and subtract 1 from that, and you'll get your degrees of freedom. So yeah, n is just the number of participants in your study, -1 equals degrees of freedom. And here's that table I mentioned. So just take a moment to look at this table. You can see there's a lot of stuff going on here. It's a very long table, and you can see I actually had to cut it in half to fit it on the screen. But on the first column you have degrees of freedom, 3, 4, 5, 6, and so on. And then on the right side of the screen it continues with 13, 14, 15, then all the way down. So that's the first column. The second column is for one-tailed tests, and then the third column is for two-tailed tests. Now I'll get into detail what this one-tailed and two-tailed stuff is all about, but for now just ignore the one-tailed column. We don't really use that as often. The two-tailed column is usually much more useful. So if you just take a look at this, all these values you see here, these critical t-scores that you see here, are for when you set your alpha level to 0.05. So the degrees of freedom, like let's just say for example you have a sample size of 4. If you have a sample size of 4, then your degrees of freedom is going to be 3. And then the critical value of t for that two-tailed would be 3.182. So you'll want to compare your t-score to the value of 3.182. That's how you determine if your observed t-score is significant. You just make that kind of comparison. Is your observed t-score greater than the critical? But that whole issue with tails, I said I would describe what that's all about. So two-tailed or non-directional tests are the most common. That's when the critical region, so to say, is on both sides of the distribution. Just think back to how distributions work. You have the mean score in the middle, and then the extreme lows go off to the left, and the extreme highs go off to the right. So what we're basically asking with a two-tailed test is, does our result fall into these extreme areas? Does it fall far away from what we would expect if the null hypothesis was true in either direction? So we don't care if it's much higher or much lower. We just want to know, is it extreme? Would our result be extreme if the null was true? But a one-tailed test, now it matters. It matters if your result is in the extreme high end of the distribution or if it's in the extreme low end. Because the critical region now is bunched up either at the high end or the low end. So you have to specify before you even begin your hypothesis test. And that's partly the reason why we don't use it as much. It's just, there's a lot of reasons why the two-tailed tests are better. You know, if you think about it statistically, it just makes it harder to get a positive result in either direction. But if you do get a positive result, it's much more convincing because you didn't have to specify which direction it would be. So, like I said, there's those three different kinds of t-tests. The first kind is called the one sample t-test, or single sample t-test. That's when you compare your sample mean with a hypothetical population mean, and then you provide some interesting standard of comparison as a result. So here's the formula. You can see if you look at it, it's basically the same, except instead of m1 minus m2, now we just have a single m, and then we have that funny looking u thing with a 0 on it. That u thing is called a mu, and the 0, that refers to the null hypothesis. So what the mu sub 0 thing basically means is if the population mean, because the mu refers to the population mean, if the population mean was what we would expect if the null was true. So in other words, if the null was true, what should that value be in the population? That's the whole idea. So we're comparing our sample mean to what we think would be in the population if the null was true. So yeah, once again, that mu sub 0 is just based on the null hypothesis. So let me just give you an example of how this kind of test could work. Let's say you're a health psychologist and you're interested in the accuracy of college students' estimates on the number of calories in a chocolate chip cookie. Maybe you're a nutritionist or something. So what you do is you read the previous research and you get a pretty good idea of what you would expect to see in a normal population, and you use that to define your hypothetical population mean, you know, that mu sub 0. So you assume that that's a value of, I don't know, 250 calories. Now what you want to know is your sample different from this population mean that you are assuming? So what you do is you go out there and you collect the data, you know, ask your participants, you know, college students, well, how many calories do you think is in this cookie? And you get an observed sample mean of 212. So now we have mu sub 0 and we have m. We have those two values. So now all we're missing is that last value. We'll talk about that last value later, but just to make a long story short, we compare our population mean to our sample mean, hypothetical sample, you know what I mean. Sorry. Anyways, we do all that math and we get t-score, an observed t-score of negative 3.07. And we compare that to the critical t-score for our study, which was 2.26, and you already know. You know that our t-score, our observed one, is more extreme. You know, it's larger. It doesn't really matter if it's positive or negative because we're doing a two-tailed test. So 3.07 is greater than 2.26, therefore we would reject the null. We have found a statistically significant difference here. So that's the basic idea of that one sample t-test. And then you have the dependent samples t-test. Sometimes it's called the related samples or the paired samples test. That's where you just compare two means for the same sample being tested at different times or under two different conditions. Here's the formula for that. it looks very similar to what we've seen before, but now we have all these little D's everywhere. The D stands for difference score. And this difference score is going to be determined by measuring the same group twice. You know, this kind of design would be the most appropriate if you're doing like a pre-test, post-test kind of study, or like some kind of within subject study. So we have a mean difference score for our sample. We have a mean difference score for this hypothetical population average. And then we have also a difference score for the S sub m you see down there. So let me give you an example for this one. It's pretty much the same thing. The math is very similar, except now we're looking at difference scores, right? So we have to measure the same group twice and compute some different scores. So let's say you're that same health psychologist and you want to try to train people, train college students perhaps, to improve their estimates about how many calories are in various foods. So to test the effectiveness of your short training program you're developing, you conduct a pre-test, post-test study in which 10 participants were asked to estimate the number of calories in a chocolate chip cookie before and after they received that short training program. So the whole idea here is if the training program helped at all, you should see their scores change. You should see a difference in their scores between the pre-test and the post-test. And in this particular study, what you found was a mean difference score of 8.5. Now, the other value, the mean difference score for this hypothetical population, remember that's still being based on the null. So the null hypothesis in this case would be that the training program won't make a difference. So that hypothetical population mean difference score would be 0. So we're just asking, is 8.5 statistically significantly different from 0? And upon calculating the t-score, we get a value, an observed t-score of 1.11. And when we compare that to the critical t-score, we're going to find that's not statistically significant. I don't even need to look up the critical t-score because just take a look at this. So our observed t-score is 1.11, but let's go back to that table. So if I go back to the table real quick and I show it to you, you'll notice something. None of these critical t-scores get that low. The lowest critical t-score on this chart for a two-tailed test is 2.064. So you don't, unless you have an extremely large sample, you don't even need to look it up in here if you get a score less than 2, because it's most likely not going to be statistically significant. All right, so we have the dependent samples test, and then there's that one sample that I mentioned earlier. But then the third kind of t-test is called the independent samples t-test, or independent measures. And this is pretty much like the classic version of this test, because this is where we actually have two means. You know, we're not just making some assumption based on the null hypothesis. We actually do have two means. We have two separate samples, and we've computed a mean for each one. So here's the formula for that. So mean for sample 1 minus the mean for sample 2 divided by the S sub m. So yeah, whenever you do a between subjects design, this is the version that you're going to be using. Like if you want to compare males to females, or you know, treatment group A to treatment group B, or experimental group to control group, or anything like that, this is the design you're going to be using. And as you might expect, if your samples are very different from each other, if you get mean scores that are very different from each other, then it's most likely going to be found to be statistically significant. You're probably going to find a observed t-score that's greater, or to be more accurate, more extreme than your critical. But let me just give you one more example. So now you're that health psychologist and you want to continue your studies. You want to compare the calorie estimates of people who regularly eat junk food with the estimates of people who rarely eat junk food. Like maybe your idea is that people who eat a lot of junk food, they're just not aware of what's going on, perhaps. So you get these two groups of people and you measure them, and you find that the non-junk food eaters get a score of 168.12, whereas the junk food eaters get a score of 220.71. So the junk food eaters are estimating that this cookie has more calories in it. So that would seemingly go against your whole idea, but that doesn't really matter so much because we're doing a two-tailed test, right? Like we don't really care which group is higher than which. We just want to know if they're different. That's the whole idea of a two-tailed test. So we calculate our t-score. We get a value of 2.42. So if you think back to what I was saying about the table earlier, that seems like it might be significant. So we want to compare our observed t-score of 2.42 to the critical t in that table, which in this case would be 2.13, and that means we found something. You know, our observed t-score is greater than the critical. Therefore, we have a statistically significant difference between these groups.